And I've got two that my goal is to get these guys done. They're 9 and 10 essentially. And then after that, I'm going to do, God, what is the name of that thing? I'll look at it right now. The moments of inertia, evidently. That's something to do with twisting, I was told yesterday. Right. And so we'll look at finding moments of inertia. But let's go back to finding centers of mass. So this is basically 9, but I've cut out some of it. The region D, the lamina, is basically a circle. And it's a circle radius 3. And if I wasn't sure of that, I could put it into Desmos and I'd find out. And we're being asked to find the center of mass, which is fine. But normally you'd expect to be told the density function. And sometimes they tell you it's x cubed, and sometimes they tell you it's kx cubed, you know, and things like that. But not this time. The density function at any point is proportional to the square of its distance from the origin. You can tell some engineer got in this bit. So when you say something is proportional, you mean it's k times that something. Right. Now I need to know what the distance of any point, call it xy, to the origin is, and square it. Okay, what is the equation for the distance of a point xy to the origin? We'll call it d. Not meant to be a trick question, it's actually quite straightforward. What is the distance from the point 0, 0 to xy?
It's the... Please go ahead, Sal.
Wouldn't it be the square root of x squared plus y squared?
You nailed it. And since they want the square of the difference, doesn't that come out much nicer as that? So what they did here is, didn't they hide the density function from you by not telling you, explicitly what it was, but telling you how to calculate it by describing in terms if it was directly proportional or proportional. I use the word directly. I must have picked that up from school when I was in Scotland. Do you use the word directly proportional as well, or do you only call it proportional?
Depends on where you're from in the US.
Is it? Okay, so some of you know what that is. So if I say word directly proportional, you just drop the word directly if it distracts you. And there is another one, isn't there? Inversely proportional. Now, if it had been inversely proportional, I know it wasn't this case, if it had been, wouldn't the answer be 1 over the, well, not 1, k over x squared plus y squared? Isn't that what inverse means, right? It's k times 1 over the thing, right? So there are only 2 guys in the world, directly proportional, k times the thing, and inversely proportional, k divided by the thing, right? Now, we have a d, we have a density function. If I employ these integrals, I will eventually get x bar and y bar. But have you noticed there's a lot of circular stuff going on here? D's a circle. Wouldn't it be less work to do the same question, but to do it in terms of polar? Okay, so here goes. The mass is the double integral of d, the density function, dA, right? Now, if you convert this integral, but change it into polar, won't the circle become theta equals 0 to theta equals 2 pi? So that's good. R equals 0 to R equals 3, that's good. K times, what will x squared plus y squared look like if you do it in polar
that would
form?
be r, that would just be k times r squared r dr d theta.
Right, so k times r squared, and then times r dr d theta. Do you agree that's probably going to be a much easier integral to calculate than if I tried to do this integral using x's and y's? I mean, just think of what the limits would be. Negative 3 to 3 for the x's is okay, but wouldn't the y's be some ugly square root to some different ugly square root? That would be very messy, not pretty. So I wouldn't do it if I could avoid it. So it's going to be the integral from theta equals 0 to theta equals 2 pi. I'm going to give this guy to theta. And that means that it's going to be the integral from r equals 0 to r equals 3 of r cubed. Are we comfortable about you can split this guy because everybody's numbers? This fella here ends up being 2 pi k. And this fella here ends up being 1/4 I to the 4. So it's 1/4 3 to the 4. So it's 81 quarters. So it looks like I'm going to have 81 pi k over 2. As I do things, keep check on my ability to screw up calculations. Does that look good? Right. So I put a little box around that because I know I'm going to use it. Move on to calculating the moments. M of y then is going to be the double integral of x times my density function dA. Well, I'm going to do this as polar. So this guy is going to be from 0 to 2 pi again. And this guy is going to be from 0 to 3 again. This fella is, well, we just had him a minute ago, he's r squared, right? This guy is r squared. This turns into r dr d theta. And what do we do about the x? Because that has to be incorporated.
That would be another r cosine.
And I'm going to separate these things and tidy them up at the same time. And there's a k in here, which I've kind of lost, so I'll put it back in. Right, there should be a k here. So I'm going to have a k cosine theta. And the integral from r equals 0 to r equals 3 of r to the power of 4. This guy gets you sine theta, so it's going to be k times. Ooh, that's interesting, but not nice. I'm worried. Why am I worried?
Because then you'll end up with a big fat 0.
Yeah. It is x, and x is r cos theta, and it's put up there. But that doesn't match the answer because I have the answer here and it's not got 0 in it. Can anybody see where I went wrong here? This, I don't worry about. This here. Right, let me look at what they said. Okay, we're good. We are good if this thing was a whole circle. So it's going to be the whole circle then. Nothing times this guy, which I don't really care what this guy is. So the answer is 0. Yeah, what was the, if you're wondering what the problem was, in my question, it wasn't the whole circle they wanted to know the center of mass. They only wanted to know one piece of it. So that's why I'm getting a 0, which actually makes perfect sense. Wouldn't you think the center should be right at 0, 0? So I'm okay with that.
I did something similar once because I was doing one of the homework problems and I think I ended up making the limit like from 0 to pi when it needed to be 0 to 2 pi. So you're not the only one, Professor Robertson.
Yeah, but you would think I would do it less as I get older. I don't. Right, this one here, I don't know about this one here. This one might actually be a number, so I'm happy with that. So it's 0 to 2 pi. The integral from r equals 0 to r equals 3. Isn't r going to be turned into r sine theta? And this guy is still going to be r squared with a k. And then an r dr d theta. So we're going to have from 0 to 2 pi r sine theta. Ah, good. That's nice. Interesting. Very interesting. I like this question, even although it's not exactly the one that was written down. I like this one. 1, 2, 3, 4. K. Where's my K? Here it is. There we go. 1, 2, 3, 4. Got my sign. Okay. This guy is negative the cosine of theta, evaluated at theta and at 2 pi. And this fella is going to give me 1/5 r to the 5. God, that's 243 fifths. And if you plug this guy in and plug this guy in, let's see if it is what I think it's going to be. Negative the cosine of 2 pi. Take away means add the cosine of 0 times 243 fifths. And that
So
guy...
it issue because cosine of 2 pi is 1 and cosine of 0 is 1. So therefore we again have a big fat 0.
Huh. But in a way that was okay, because I was hoping for an origin. So if you take that shape, is it a surprise that if the density function is directly proportional to how close it is into the center, aren't you getting lots of circles of greater and greater density? But aren't all of them still going to balance at the origin? So that does make sense to me physically. That for that shape. Now, if you had changed, this is the density function that we did use, right? It ended up being that guy. But if you did it inversely proportional, it would look like that. You would end up with different looking math, but where would the center of mass be if you used the whole circle?
The same place, the origin.
Same place. And isn't it due to the symmetry of the way this is created? Now, if you actually did the question that they only wanted this piece. So that would be 0 to 3, 0 to 3. Now, what would the change be? Well, wouldn't this go from 0 to pi upon 2? And wouldn't r be 0 to 3? So if I went back to all the integrals that I've just done here, right? That would turn into pi upon 3. That would turn into pi upon 3, and the other one, wherever it's gone to, would turn into pi upon 3. Wouldn't the difference be that these would not be 0 anymore, and you'd get a point? My guesstimate would be, if you wanted this shape, wouldn't you probably get something kind of about there? And that would have worked as well. So for the next one, I'm going to do is their guy. And it's a nice messy one. The region D is the area between these two semicircles and the bits of the x-axis that join them. We're being asked to find the center of mass, and the density function is inversely proportional to its distance. So this guy is a circle, if you rearrange it, that looks like that, and goes like that. And the other one is another circle, which if you rearrange it looks like that, and it looks like that. Since it's positive, it's only the top half, and they talk about joining it with the x's. They're basically just saying do that. So this is the shape for D. Are you comfortable about how we created the shape based on the fact that these are positive square roots? If these had been negative square roots, right, negative the square root of that and negative the square root of that, what would be my shape in that situation? What would it look like if it said negative this square root and negative that square root?
It would
Positive.
be flipped over the x-axis.
Yeah, be down here. So far, so good. Now, I know I've drawn this picture kind of wonky, but can you pretend I drew it better? I am going to make a prediction, and then I'm going to get proved right, because I'm going to have to be right sometime. I'm going to make the prediction that X bar is 0. Now, I may be right and I may be wrong. Why do you think I'm going to go that way? Why do I think X bar is going to be 0 in this shape?
Because the symmetry across the y-axis.
Yeah, that's what I'm hoping for. Now, that doesn't always work, because if you make the density function heavier on the right and less heavy on the left, won't the center of mass move a little bit to the plus side of the axis, right? But I'm assuming that nothing nasty like that is happening. So that's a prediction. We shall see if I get lucky. Now, we have a density function here, which is proportional to its distance, inversely proportional to its distance. Let me reread that carefully. Yep. Now, if you're inversely proportional to the distance, you're that guy. Great. Not the distance squared, but the distance, right? And doesn't that turn into K over R? Right? You comfortable with the density function is K over R when you go polar? So the mass is the double integral of D, density function, dA. In this case, it's going to turn into, well, we'll set that up in a minute, but the density function is K over R times R dr d theta. Okay.
Again, that just gives us K, which is way less nasty than I thought. I was for a brief second very worried that we were going to have to integrate a natural log.
Oh God, that would have been horrible. Agreed. I'm glad that is the case as well. Now, how do you describe D? Because we have to do it in terms of polar, right? What would be the R range for this shape? R from what number to what?
It would be when, let's see, are we talking, well, we're talking the one shot. I was going to say 1 to 3.
Correct. What is the theta from what to what in this story? So imagine you're generating this shape and you're returning it until you got to this shape.
0 to pi.
Agreed, everybody? 0 to pi. So this is going to be from theta equals 0 to theta equals pi. This is going to be R equals 1 to R equals 3. Before we do the next line, do you know you do not want to do that question using X's and Y's? Would you agree that that question would be really ugly if you try to do vertical rectangle? Oh God, I'm glad we're not. And wasn't expecting this, but I'll take everything that we can get. It's from 0 to pi. It's from R equals 1 to 3, but basically it's just K, which is what Sally was talking about. I would separate that out because it looks to me like it'd be much easier to do that way. And so it's going to be the integral from 0 to pi. Who do you want me to give the K to? Do you want to go to the theta? Do you want it to go to the R? Got to give it to somebody. Who do you want me to give theta to?
You know, theta got the cookie last time. Let's give R a cookie.
Okay, so it gets 1. And this guy he gets the k. Right, if you do this guy, you get pi. And if you do this guy, you get 2k. So the answer is 2 pi k. Put a little box around it to remember it. So we do the moments around x. And that's going to be the double integral of y, density function, times r dr d theta. And theta is going to go from 0 to pi, and r is going to go from 1 to 3. And too late now, but shouldn't have rewritten that guy in terms of r and theta. So I'm just going to do it in the next line. So r is going to be r cos theta or r sin theta? R sin theta. They cancel out, and so you've basically got a k here, you've got a dr, you've got a d theta. And this time I can split things. The thetas can get the sine theta, and the r's can get the k. If you integrate the sine, you get a negative cosine. And you evaluate it from 0 to pi. And if you do this guy, you get 1/2 r squared. Evaluate it from 1 to 3. Okay, cosine of pi is nothing. Take away -1 ends up being 1. 9, is it?
Cosine of pi would be -1, so that would be 1 minus 1.
Are we sure? Let's write that down. So it's going to be
Yeah, because we have
negative
negative cosine.
of
Cosine
pi.
of pi is -1.
And then that guy, right? And this is nothing. 2 nothing. 2 then make positive. No, I think it's 1.
Cosine of pi is -1.
Cosine of pi is -1.
Yep.
And the negative of -1 is 1.
Oh, darn it. I'm trying to tell you you're wrong and you're right all the time. There you go. But at least it ain't 0. That's why I was, I don't know what. Right, you plug this guy in, you're going to get 9. You plug in 1, you're going to get 1. 9 halves, take away 1/2, leaves you with 8 halves. So that ends up being 4k. And therefore I get 8k. Is 8k looking good, guys? Got no done that good. If we do the my guy, it's going to be theta equals 0 to theta equals pi, r equals 1 to r equals 3. The x fella is going to become r cosine theta. Then you've got k over r. Then you've got your r dr d theta. And that's going to split. How's that going to split? I'm going to take this guy here, integrate with theta, and I'm going to take this guy here, which what cancels down to be kr. Check that again. R times k, yeah, kr. Well, I've already done that guy, can't I? Just take that and call him 4k. Because we've done it here. And what about this fella?
That will be a big fat 0.
Oh, okay. Now, almost finished. Is an x bar that fella, and y bar that fella. And this guy is 0 over, I put a box around it, 2 pi k. And this fella is 8k over 2 pi k. And the k's cancel and the 8's partially cancel, so you get 4 over pi. So 0, 4 over pi. Hey. Yay. Isn't it nice when what you think should happen goes and happens? I think the symmetry is what caused that, right? But don't make the assumption that it is 0. Because, you know, if you do that, you might get 3 questions right and the 4th question's wrong. And the reason it's wrong is because, as I said earlier, if the density function makes this side heavier than that, won't the centre of mass be further to the right? And so it won't be at 0 anymore. So that's kind of how you have to do it, even if you're 99% sure it's still going to work. Now, what is 4 over pi as a number? 4 divided by pi is about 1.3. Well, I know that's 1, so 1.3 is just a little bit above it. It's pretty stable. Is it possible to have a centre of mass outside D?
If you did, then you would do something, then you probably did something wrong.
You would think so, but it is possible. I'll show you a simple example. Suppose I'd done that shape and I made it a perfect circle inside another perfect circle. Do you know the centre of mass would be the origin? Strictly speaking, isn't it not inside D?
I mean, I suppose technically because it's a washer.
Yeah. So even if it's a shape that looks like this, I could make it, you know, if I got the right combination of density functions, I could make the centre of mass there. It is possible. I couldn't do it off the top of my head. At least if I tried one, the math would be horrendous, but it is possible. Do you know where our human beings, us guys, do you know where our centre of mass is? Right in the centre of our pelvis. Now, it kind of makes sense that you'd have a centre of mass somewhere. It's kind of interesting that it I guess through evolution or whatever, that the centre of mass ended up being that way. Can you imagine if human beings had little tiny legs and big top torsos? Wouldn't that be an unstable shape to walk upright in? Can you see that just through evolution, wouldn't we get bigger legs? Because creatures that can move quicker can catch food and run away from things that want to eat them. So, you know, where am I going with this? Evolution tends to make solutions to problems. And those solutions, in some cases, could be thought of just like we did here, mathematics. Now, this new guy in town, where on earth is he? I'm looking for the formula because we're now going to do moments of inertia. And I know I've got a formula because I wrote it down somewhere. I guess I could write it again by trying not to. There it is. Gotcha. You just write these guys down for tests and exams and anything else you want. This is the formula for finding the moments of inertia, which is something to do with twisting forces. These are for two-dimensional situations, right? And so the moment of inertia in the, I don't know if it's on the x-axis or rotating in the x-axis, because that would be 2 different things. But this is the moments of inertia in the x. This is the moment of inertia in the y. And there's another moment of inertia, which is what you get when you add the 2 of them up. So evidently, this is how you calculate the twisting forces on some kind of object based on the density function pushing down more on one side than the other. And so that has a tendency to 20 twistings. That's my best guess at what's going on here. But don't tell your physics teacher because he'll laugh at me. Okay. So
For those formulas, are they both supposed to be with the dy at the end?
No. The x's gets y's and the y's get x's. Yeah. I believe that's so. Let me, don't quote me until I've checked it. The x's get a, well, strictly speaking, you get both of them. So it doesn't really matter. I should have probably called it dA then. Let me do that. I of x is the double integral of y squared, this fella, dA. dA is good. Can't you use dA to mean dx dy or dy dx, whichever one makes more sense to you? And this one gets you that. And the overall inertia, which is, I think what that means, is just add the two together. Okay. Now, if the shape that, if D happens to be circular, won't you convert them into polar? But if D is rectangles and all sorts of other things, then we just leave them alone. First one, thankfully, is relatively simple. Version of 12. D goes from 1 to 3. That's in the x's. And it goes from 1, in my case, to 4 in the y's. So we're talking about basically a rectangular plate. And the density function is given to us, and it's just k times y squared. Right, so if you were looking at this shape, since the density is k times y squared, wouldn't each strip be the same density, but wouldn't it be getting denser at the top and less as you go down? So this shape is top heavy. So I'm assuming that if that's top heavy, the rotation is probably going to go like this. Right, there's a tendency to fall this way, right? Or that way, right? I wonder what that will look like then when we calculate it. So this fella is going to be the double integral of d y squared density function dA. In this case, the x's go from 1 to 3, and the y's go from 1 to 4. And then we have a y squared and a density function ky squared dy. Oh, by the way, in these questions, the k does not disappear. Remember when we did x bars and y bars, the k's always, leave the building. In these ones, they stay put. In this particular question, I'm going to give this guy the k. And this guy. And keep all the y's. So this guy here becomes 2k. And this guy is 1/5, oh, darn it in space, 1/5 y to the 5. Okay, that's 1,024 fifths. Take away 1/5. 1,023 fifths I make it. Okay, somebody do a calculator on that. Rosie, question.
How were you able to tell that the lamina is top heavy?
The density function is a multiple of its y coordinate. So the bigger the y coordinate, the denser it is. So it's top heavy because of that.
So how do you know that the top is heavier than the bottom?
Well, the y values at the top are 4, so the density is going to be about 16k. The bottom of the rectangle only has a y value of 1, so its density is only going to be k times 1 squared. So at the bottom, the density is k, but at the top, it's 16k, right? It's heavier at the top than it's at the bottom.
Okay, so if the exponent was negative, could that mean that it's heavier on the bottom than on top?
You wouldn't get a negative because the density function has to be positive. So
Okay.
k has to be positive. But you could make it go the other way, couldn't I? Call it 1 over y squared. You know, if the density function was k over y squared, wouldn't the top be quite small and the lower down would be relatively bigger, and that would make it bottom heavy. If I did it as kx squared, wouldn't it be more to the right being heavier than it was to the left if it was kx squared?
Okay, thanks for explaining.
Is that guy correct?
Yep, and when you combine those, you get a total answer of 246K over 5.
Okay, a ridiculously ugly number, but at least we don't have as much work to do. Would you agree it's just one integration done, right? There's not, you have to do m and then divide it and other things. So for that, I'm a little bit grateful. Now, if we go for the other one, it's going to be the double integral over that region D of an x squared. That guy. In this case, it's going to be from 1 to 3. And in this case, 1 to 4. It's going to be x squared times ky squared dy dx. Thankfully, the variables are separable. So yeah, I'll give this guy just the x squared. And I'll give this guy the k. Okay, this is 1/3 x cubed, so it's going to get you 9. And then it's going to be 9 take away 1/3. So that's 9, 27, 26 thirds. And this guy's going to be 1/3 k cubed. I'm just not going to even attempt that one. Four, 16, 64 thirds. Take away 1 leaves me with 63 thirds. 63 thirds is actually 21. So this guy ends up being 26 times 21. Oh, wait a minute. Those cancel. Get you 7. Okay. So 26 times 7 is 182k. Does that look good?
Okay, I'm sorry. I am not tracking how with the I sub y, we got the, how do you know that's supposed to start with x squared?
It's a formula. It's always x squared.
Thank you, sir.
Right. So these guys are these guys don't care what the question is. It's the same formula every time. Okay, we are done. Well, almost. Don't you just add these two together because you want to find all three? The first number I got was 2046 fifths k, and the second guy I got was 182k. And you stick them in the calculator and you do all your other stuff and you get that. So the moment of inertia of this plate using that density function is 591.2 K. I think the reason why K exists is if this plate is much heavier, won't that force increase? Right? You know, if K was a really big number, the difference between the top and the bottom, although ratio is the same, numerically they would be different. So that's my excuse for why K's is still there.
If you want, if anybody wants to add a improper fraction like WebAssign would like, the answer is 2,956 fifths K.
What's on the bottom? 2096, and you said something on the bottom.
2000, it's 2,956 over 5.
There you go, if you want it that way. Are we okay with that first one? How to find things called moments of inertia. If you're never going to be an engineer, which I am never going to become an engineer, isn't it just an exercise in plug and chug formulas with double integrals? And that works perfectly fine. We don't have many of those guys, so I'm going to show you, or at least start, since we do have 5 minutes, I want to use your time wisely. Here is back to center of mass question. And D is described as a lamina, right? The shape that is inside this circle and outside that circle. And we have to find the center of mass if the density at any point is inversely proportional to its distance from the origin. Well, we already know that jargon. They just mean K over R. Would you agree that these are definitely circular-like? So this question should be done using polar. So if I can find one, hopefully I've got it handy. I do. Good. I'm now going to show you why Desmos is so good. That's what that shape looks like. The blue one was the x squared plus y squared equals 6y. And the green one is the x squared plus y squared equals 9. And they want this piece up here, right? See, it's outside the first circle, but inside the second, right? They want this shape here. So all I'm going to have time for today is to set up the polar coordinates of that shape. So are you happy about, Desmos makes drawing these shapes 9 times easier than if you had to try and figure out what x squared plus y squared equals 6y looked like. Now, we need to set up limits of integration for the r and from the theta. If you take the origin, as you always do, and you project ray lines, like these guys, do you notice that the r value starts here and it always finishes here? So the limits of the r are relatively easy to find. Now, I don't have the picture handy anymore, but can you trust me that this circle has a radius, say, 3, right? And this one here, right? So you're looking for this guy to this guy. Okay, now what about theta? Also, by the way, that inside radius, right, and the outside one is based on the circle. What about thetas? Well, if you want to do theta, you need to know these two. Time. Okay, I need to find out what angle that line is and what angle that line is. So I need to find out where this guy intersects with that guy, but I need to understand what it is in polar. Now, if you equate these, isn't 6y equal to 9? Agreed? And so does it not make y 3/2? So what you're trying to do here is find this point that I'm looking at. Now, this point here has a radius of 3. So what do I know? I know this has a radius of 3. I know the y value is 3/2. Can I now find the angle? So won't the sine of theta be opposite over hypotenuse? Which means that the sine of theta is what? Is 3/6. So isn't the sine of theta 1/2? Oh, that makes it pi upon 6. So I know that it goes on this side at pi upon 6. Can you trust me on the other side here, what it would be? When you just find the y value, but it would be a negative, well, by symmetry. If you know that one, don't you know this one? So the other one I'm going to say is 5/6, even though I'm not doing it through algebra. And I've run short of time. So remind me tomorrow to do that one from scratch again, okay? But at least you got a basis of how to start it. If you have a shot at it yourself as well. Because once you've set this up, isn't it just use the formula from that point onwards? Okay, I'm going to say put your last name down and bye-bye. And I'll hang about for any questions. And I'll see you tomorrow, if not.
See you tomorrow.
Thank you.
I had a question about one of the homework questions, and I think I'm doing something wrong, but I can't find where it is.
Okay.
Can I screen share?
Sure.
Or can you enable screen sharing?
This should be done now. Can you do it?
Okay.
Come on. Yay. Oh, well, we've got all sorts of things going on here.
Gotta open up the file. Okay. Why is it taking? Just open it. Oh my gosh.
You now, you're living in my world. You know when I complain about Windows and things? Tess, can you see what my world is like sometimes? Right? I'm having the same issue. So I feel your pain, Rosie. Right.
I had it. I like added this to my desktop.
Well, yeah. Well, load it up and then share the screen, and I'll be able to see it. Is it loaded up or not?
No.
Oh, okay. Then
Let me open it a different way.
you're off this week, aren't you, Tessa?
I actually worked Monday through Wednesday, but my dentist loves taking time off. So I had vacation all last week, and then I have the rest of this week off. So it's pretty nice.
Well, it's nice that he makes lots of money out of fixing people's teeth, but it can't be good for you financially unless he pays you.
Yeah, I have some paid time off, so it ends up working out, and I have so much math homework to do. So I actually really appreciate having some extra
Okay.
time.
Okay,
Right.
is this readable?
Yes, it is. So,
Okay.
so you're looking at a straight line meeting a quadratic, and the intersection points are at -1 and 1.
Yes.
And the quadratic is from y equals x squared on the small side to y equals the straight line x add 2 on the big side. Looks good. Okay, and I'm assuming the density function is kx squared. So far, so good?
Mm-hmm.
Right. And so you got the mass as 46/7 k, and they told you it wasn't right. So let's go hunting for it. 1/3 x cubed looks good. If you do 1/3 x cubed, you get not what you wrote down.
Oh my gosh.
So the x cubed plus 6x squared plus 12x plus 8 is not correct.
Wait, so I didn't change the power to 4 when I integrated.
Well, it's not even
Or-
that. The problem happened before that. X plus 2 cubed is not what you have written it down to be. X plus 2 cubed is x cubed plus 2x squared plus 4x plus 8.
Oh,
So you
factored
foiled it wrong.
wrong.
Yeah.
I
So that's
foiled
where it went wrong.
wrong. Okay.
I'll show you a little trick that you might want to use. I'll show it anyway, and you can tell, whether you want to use this. And then I'm going to have to leave you because I've got another class. So I've lost you. I've lost my window. Right. I know where it is.
Go to the Zoom icon at the bottom of your screen.
I don't even, I have it now. Right. So I should be able to do the share. Good. Right. There we are. Right. A little guy called Pascal's triangle. This is the trick. Do you know sometimes you want to do ugly things like that or that, right? Occasionally you have to do things like that. Pascal's triangle. You go like this. And the ones that matter are this is something squared, this is for something cubed, and this is for something to the power of 4. So if I wanted to do x plus 3 to the power of 4, I would use this guy, and it would be, well, 4 would be this one, I should say. So you get this guy to the power of 4, and then you get 4 lots of this guy cubed in one of them, and then you get 6 lots of this guy squared and square of them. Then you get 4 lots of this guy and that guy cubed, and then you finish with 1 lot of that guy to the power of 4. And that's x plus 3 to the power of 4 once you tidy it up. It's called Pascal's triangle. If you make a lot of mistakes on higher powers, and maybe this would be a way that might reduce your mistakes. And if you see it in full, it says this. Well, for this one, it says it. 8 to the 4 plus 4a cubed b plus 6, because of that one, a squared, b squared, plus 4ab cubed, and finish with a b to the 4. What you notice is that every power adds up to 4. And you get the coefficients from this row. So if you're doing the cube one, this one here, and it would be that one, right? You would say x cubed plus 3 lots of this guy. Well, let's do 3x squared plus 1 lot of this guy plus 3x, 1 lot of this guy squared plus this guy cubed. And that's what you would get if you tidied that up. It's a little trick. If you like it, you can use it. If you don't, I understand. Right, bye-bye, guys. I'm out of here.
Bye, thank you.
Thank you.
Later.